In the next couple of videos, we're going to look more deeply at flow simulation. We're not necessarily just going to stick with the mechanics of how to run the various software tools. That will be part of it, but we're also going to start off with the notion that a flow simulation, in order to be valuable, has to be correct and accurate. And by correct and accurate, that means it has to numerically predict lift and drag in the case of an airfoil, drag in the case of a lot of objects, those sorts of numerical things that we expect when designing fluid dynamic things that we can get a handle on at the outset. So in order to achieve that, let's look at an airfoil. Now, airfoils, or airplane wings if you want, have been studied probably more than any other fluid mechanical thing over the past 120 years. And there are a number of really important results that have enabled the design of aircrafts. And aircrafts were flying before fluid dynamic simulations existed. What they were based on were model tests, and model tests in wind tunnels, model tests in tow tanks, where scale model airfoils in very simplistic form were evaluated, lift and drag measurements were made and tabulated. In addition, there was several two-dimensional and then three-dimensional theories that were developed to predict the behavior of airfoils. And those have become very, very accurate. Now, if we are going to be able to trust our flow simulation, we should be able to reproduce the results from all of that history. So in this series of videos, what I'm going to walk you through is, first of all, a basic intro to the theory of an airfoil, to the point of giving you some appreciation for what we should expect to see in the results from a flow simulation. Then we're going to move on and do some quick calculations of one particular airfoil based upon the NACA series of airfoils, and we'll talk a bit about that. And then finally, we'll try and do a simulation of that same airfoil using both SOLIDWORKS and ANSYS, and see if we can predict or come up with the same results that all of the history of that airfoil tells us we should see. At the end of this, we should have a better appreciation for some of the pitfalls and some of the things to watch out for in flow simulations. So let's get started. I just love listening to that guy talk. Let's do an introduction to airfoils and lift. So we're going to talk about airfoils and hydrofoils. They're both kind of the same thing. And if you think of your typical wing, then we think of basically a straight thing with air blowing over a leading edge, over top and underneath it. And the further you get away from the wing in the vertical, the less of an impact it has. So you start to see more straight streamlines. But let's focus in on the two-dimensional cross-section of that wing. And just looking, if we look at other sections along there, along the length of the wing, in the middle it flows kind of like a two-dimensional one, but on the wingtips, we get this wingtip vortex that's really interesting and tightly coupled with the performance of the wing. But there's also another vortex at the trailing edge, which really is the reason why lift occurs, is that trailing vortex. Now in two dimensions, it's essentially important to think about a two-dimensional cross flow coming from the right-hand side, and then you've got this funny shaped wing thing. We're all familiar with the shape of a wing, but the key thing is it's got a trailing edge, which is pointy. It's very sharp, and it has to be sharp. We've got a leading edge that's blunt, and it's more or less blunt, but it has to be basically blunt. Those are the two key features in what makes a wing work, actually. And so with a wing at 0-degree angle, we've got uniform or symmetrical flow top and bottom. Just as much airflow goes over the top surface of the wing as the bottom surface. Because of symmetry, if you integrate the pressures, you come up with a net zero. So there's no lift force on a symmetrical wing at 0 angle, but there is a drag force, and the drag is caused by pressure drag at the front and by skin friction drag all along, and that drag force is not equal to 0. So that's the basics. Let's look again now at a different kind of wing. Take the same cross-section and tilt it at an angle. The angle is referred to as alpha, or the angle of attack frequently. And that's typically 0 to 20 degrees for a real wing. And let's look at what happens if we do an ideal flow around that. Take the same situation of top and bottom are equal mass flows, and you've got streamlines which over the top have to turn up and around, and then somewhere downstream we should expect that the airflow would look the same as it did before the wing was there. But there's three key points that are a problem, and these are places where the air needs to make a sharp turn, and that's a challenge. So let's just focus on those 3 points. They're at the wing trailing edge tip, the sharp pointy bit. They're at the stagnation point somewhere on the leading edge, and the air has to flow around those points. And if we looked at the same mass flow above and below, then things change quite a bit. If you just take the center streamline where the mass flow is equal, you see that that wing being there has deflected the mass flow downwards because of the shape of the streamlines around it. And that means the pressure on the bottom side ultimately is bigger than the pressure on the top side, and you get a lift force. And that sharp edge at the trailing edge is what's key to all of this happening. And that sharp edge refers to something called the Kutta condition. So let's look up close at that trailing edge. First of all, consider just not a wing, but just a cylinder. And if we take flow around a cylinder, there are 2 stagnation points, front and back, where the air slows down to be the speed of the surface, and then it speeds up again, and then ends up being at the speed of the surface on the back side. Well, normally that's symmetrical, but if you then say, what if I wanted to move those stagnation points up and down? You could apply a rotation. So in potential flow, that would be a circulation. And there's a nice simple equation for that. And that simple rotation actually makes the stagnation points move, as I'm showing here, where the front one goes up and the back one goes down. And if we eliminate the sphere and just put in an airfoil shape, the flow lines around it effectively look the same. And what that means is that the flow field that we can create with a really simple source or simple potential flow actually replicates the flow around a wing quite well. So that Kutta condition at the trailing edge is what makes this all happen. And it's because the airflow on the bottom has to be smooth as it leaves that sharp edge. It can't make a really intensely sharp turn around to follow the boundary layer. And on the top edge, it has to be smooth as well. Now, if it isn't smooth on the top edge, then you start to get this little bit of recirculation and separation and turbulence. And in fact, you'll see that in simulations occurring quite readily. But it's all key to what's going on in the boundary layer, which is interesting because the fine scale behavior affects the macro scale. So a proper wing, a real wing, has those stagnation points that have moved from where you would think they were. And then it's got this third point, this separation point, which it could be anywhere on the back side of the wing. And those points help us define what the drag and what the lift are from the wing. We try to minimize the amount of separation. And so if that separation point moves further and further towards the front, we get more drag and no lift. So the wing cross-section generates the lift and the drag in these 2 directions, front and back, and up and down. And we can look at various different wing cross-sections. A straight chord or a straight center line and a thickness are key things that we look at. And the chord is the length of the wing. We could also have a curved one, which would be a wing that has camber. And so those are key parameters: chord, thickness, and camber. Camber is defined by the height of that curvature, and that's usually a percentage number of the chord. So let's look at some standard airfoil sections because they're quite cool and easily analyzed. We look at the drag force and the lift force, And using basic drag equation, half rho c squared c v squared a, where c could be the lift coefficient or the drag coefficient, and the a is the plan area of the wing. Plan area is if you looked at a wing from above, it's the flat area that you see. That's the plan area. It's different from a typical drag coefficient where you use the frontal area or the surface area. So keep that in mind. It's the plan area for a wing. If we look at the lift coefficient as it changes as you tip the angle of the wing at alpha, then that lift coefficient increases as you increase the angle of attack, up to a point where it rolls off. The drag coefficient also increases, but it doesn't start from zero because there's always some skin friction drag. And then at some point, it increases very rapidly. So those two curves of lift and drag behave quite differently. If we do a ratio of them and also plot it with angle, you'll see that the rise won't be linear as it is with lift coefficient. It will be convex downwards. And the peak of that lift coefficient to drag coefficient is typically called the glide angle. And at some point, it stalls. And the stall angle is where you get really no more lift compared with how much drag you get. Those are really important wing cross sections, the NACA and other tabulated forms. The wing shown here on an old 1930s sailboat, that still behaves as a wing, certainly, and it behaves quite well. But it doesn't really match the cross sections that are seen in those simple sections. Nor does it behave in two-dimensional form. It's actually a very three-dimensional structure. So we're not going to easily be able to analyze that. However, we can look at genuine two-dimensional types of forms. And to do that, we can use some tabulated data. And that's what the NACA wing cross-sections represent. So using the tabulated data, essentially what we're doing is we're taking advantage of the fact that over the past 50 years and more, people like you, maybe graduate students a bit past your stage and maybe research students, had spent time in wind tunnels and water tunnels, tow tanks, and flumes, taking different exact cross sections, varying parameters, and coming up with drag coefficients and lift coefficients for each of those wing sections at varying angles of attack. And so by relating the calculations using similar methods to potential flow that I've showed very briefly, and using real experimental data, models of the lift coefficient and drag coefficient versus angle of attack have been very well developed and are very accurate for particular wing sections. So what that means is if we're going to look at simulating a wing or simulating anything, we should be able to take one of the most well-studied fluid forms, and we should be able to reproduce those results. So first of all, let's have a quick look at one of the tools where we can find the data for those sections. The first tool we're going to look at is an airfoil tool for design of the profile of a typical airfoil. Now, before we use this, it's important to know that there's been a number of series that have been resulted from standard testing in wind tunnels of different airfoil shapes. And they're categorized by a rather arcane series of numbers. And this website that I'm showing actually has a really nice online tool for finding the data from this. This is publicly available data. But the way to search is to recognize that the way that the NACA code numbers work is that one of the numbers represents the maximum thickness or the percentage of thickness of the airfoil. So if we pick 6% airfoil thickness, and another one of the numbers is the camber. Now the camber is the curvature of the airfoil. A symmetrical airfoil, so with no curvature, essentially a flat plate, would have a 0%. And we can search for that, and in fact what we'd see for a 6% thickness, 0.6 would be the last two digits. For 0 camber, we would get an NACA series number 0006. Whereas if we pick a 10% camber, and we'll search all, and a 10% thickness and a 5% camber, we should come back with an airfoil that looks more like this, with that curvature. We could increase the camber to 10, and you can see that the airfoil gets more and more asymmetrical. See if we have one that's as big as 20. And so you can see that they're even more curved. Now, if we wanted to have a very thin airfoil, we could pick something much more slender, and you can see the difference there. So these numbers of thickness are how thick the actual foil is itself, and camber, I'm going to pick 0. And from all of these different airfoils, you can see that there's a whole variety of them with different series that were tested. But I'm going to just look at the NACA 4-digit series. So you can see I've got this NACA 010 airfoil, and we can look at the details of that. And this tool gives us an XY position of the curve of the shape of that, gives us a nice graphical profile, and it also gives us test data and prediction data from this airfoil under different conditions. Now you'll notice that there's a variety of plots here. CL is the lift coefficient versus alpha, or the angle of attack, and CD is the drag coefficient versus alpha, which is the angle of attack. And the angle of attack alpha goes positive and negative, and that would be different for an asymmetrical airfoil. This is a symmetrical one, so these curves are mirror images of each other. These drag coefficients vary with angle, and the lift coefficients vary with angle. However, there's multiple curves here, and that's because different flow conditions of Reynolds number dramatically affect the lift and drag results, particularly at the higher angles. So you'll see, if we were to look only at the extremes, we could see that for a low Reynolds number, or a low velocity flow if you want to think of it in air, that the lift coefficient for the airfoil cuts off at only, say, 7 degrees. Whereas at higher speeds, that same airfoil would be good to a pitch angle or an alpha of 15 degrees. That's a massive change, and it means that at low speeds, this airfoil is very, very critical to its angle of attack, which, if that was a passenger airplane, could cause real problems. So we have to know what the Reynolds number that we're looking will be. And so for the example that I'll be using in this series of videos, I'm going to be looking at something where the speed is around 200,000 to 250,000 Reynolds number. And so if I just look at that Reynolds number by clicking the choices here, that shows me the Reynolds number range, and it shows me the angle of attack, maximum lift at an angle of attack, and that's helpful in showing the results. So in this case, I've got two different models for two different maximum angles or optimum angles, and you can see I've got some good results with good agreement. So this data is as reliable as we can get. This data is validated with model testing, and so we should use this as a comparison. If we could take this profile and we could model this and run a simulation on it, that if our simulation is correct, we should be able to calculate the same lift coefficient versus angle and the same drag coefficient versus angle as this shows us. Now, one of the things that makes for a really easy comparison is the ratio of the lift to drag coefficient. So this curve of CL over CD. So at small angles, the lift coefficient is small because the airfoil is just pointing straight into the wind. But as the angle of attack increases, the ratio of the lift to the drag gets quite large. And in fact, we should expect to see a lift coefficient of around 40 times what the drag coefficient is. And that's what our simulation should predict. So we should be looking for our simulation to show over a series of angle attacks a lift coefficient increasing. We should be able to go past, say, an angle of attack of 5 degrees and see that lift coefficient to drag coefficient ratio decrease. And what's happening there is not that the lift coefficient is getting smaller. In fact, it continues to get larger, but the drag coefficient is getting much bigger, much more quickly. And you can see that in these two plots on the right. You can see that the lift coefficient increases even up to 10 and higher degrees, almost linearly, but the drag coefficient, once you get past 5 degrees, starts to increase in slope and almost looks like a parabolic curve. So that's what's causing this roll-off of lift coefficient. We should be able to reproduce that in our simulations.